In this video, we're going to be continuing our exploration into time series forecasting, and we'll be talking about one of my all-time favorite models, the AR model, or the autoregressive model. Let's just talk about the name for a second before we get into this really easy example. Autoregressive, so that means that it's a regression that you're probably familiar with, right? You're trying to predict something based on other things, but this is a specific type of regression. It's an autoregression, which means you're trying to predict something based on past values of that same thing. And that's a really powerful point that I think doesn't get emphasized enough in time series forecasting videos or courses, is that it's very natural to want to predict something. Maybe it's the price of some kind of item, or it's the quantity of something you need, or it's the number of houses sold per month, whatever it is. Of course, there's a lot of factors going into each thing, such as the weather, or the stock market, or many other different things. But what's more natural than saying, I want to predict the value of that thing today based on what the value of that thing was yesterday, based on what the value of that thing was last week, last month, last year, going back, right? Because that thing's going to change in maybe some predictable way. Maybe it's not going to be predictable at all, but chances are that there could be some pattern that emerges. And if we can capture that pattern, we can get a much stronger prediction, especially if we incorporate all those more common things that people think of when you do a regression, all these other factors. Okay, so I wanted to just give you guys a really gentle introduction into why autoregression is a very powerful concept. Now let's get into the example and how you would figure out what is the best autoregressive model for your situation. So in this setup, you are a milk salesman. More particularly, you are a distributor of milk. You ship milk all over the country. And one really big problem for you is month by month, you want to know how much milk should I produce so that I can have the exact amount, or pretty much the right amount, to ship to everyone who needs it. I don't want to have too much, right? Because then I'll have milk which is going to spoil. I don't want to have too little because then I can't fulfill all of my orders. So you want to know exactly how much milk should I load onto the truck this month. So let's say you go ahead and see if you can use time series forecasting, or an autoregressive model maybe, for this kind of situation. So the first thing you do is you go ahead and draw up a plot where the y-axis is the quantity of milk that is shipped, and the x-axis is time. So here we're saying each of these blocks separated by the purple dotted lines are years. So here's 2016, 2017, and 2018. And you make a chart of how much milk was demanded in each of those months. So each of these black dots here is a month, maybe, let's say, and you draw it out. You can already see a pretty clear pattern here, right? As you go into the month, into the year, the quantity of milk demanded goes up, and a little bit more halfway past a given year, then it dips, right? And then maybe it plateaus, and then at the beginning of the next year, it starts all over again, up and then down, up and then down. So this is a very predictable pattern that you can take advantage of to predict exactly how much milk you might need for any given month in the future, in 2019 and beyond. Now, how would we figure that out? How would we figure out? Let me introduce some notation here so we can write a model in just a second. Let's say M sub t is the quantity of milk that is demanded this month. Let's say M sub t minus 1 is the quantity of milk that was demanded last month, so minus 1. And M t minus 12, for example, is the quantity of milk that was demanded 12 months ago, or this time last year, okay? So this is our notation for quantity of milk demanded. Of course, the thing I'm trying to predict is M sub t, because I'm in my current time period. And the thing I have available to predict with are all these M sub t minus 1, minus 2, minus 12, however much I want, however much data I actually have, right? So one naive approach, you could say, hey, why don't I just throw every single lag from 1 through 12 maybe into the model? Then I'll have a great prediction model, right? Because I'm incorporating all the data that I have. Well, you might get a seemingly strong model, but it's going to be prone to a lot of statistical issues like overfitting, which just means that it's too tuned to your certain data. And besides, in statistics, in regression modeling, if a simpler model can do the job, or pretty much the same job as a very complicated model, we're going to prefer that simple model because it's going to hold up better over time. So for that reason, we want to figure out only which lags, only which of these t minus what are important for our situation. We're going to be using our good friend, the PACF chart, or partial autocorrelation function. So if you haven't seen my video on autocorrelation and partial autocorrelation, go ahead and watch that. If you really don't want to watch it, then the basics of PACF are that the PACF at a given lag, so for example, PACF of lag 1, is going to be the direct correlation. Actually, it may be better to say the PACF of 3 is going to be the direct correlation of the quantity of milk demanded 3 months ago on the quantity of milk today, without considering, so removing the effects of the intermediary time periods, which are, so we're trying to do mt minus 3 direct effect on m sub t. That means it removes the effect of m sub t minus 2, price of the quantity of milk 2 months ago, and m sub t minus 1, quantity of milk just last month. It's the direct effect. So it's pretty natural here. We only want to keep the lags whose direct effects are high in magnitude, either positive or negative. If those direct effects are 0 or statistically very close to 0, we don't want to include those lags, because if some certain lag has no direct correlation with our quantity of milk demanded today, why would we include it? It's not important. It's just going to make our model noisy and cluttered, right? So we only want to include the lags whose PACF are above these red bands. And these red bands, basically, you can think of them as anything within the red bands we think is statistically close to 0. Anything outside the red bands are statistically different than 0. So we have evidence to say that anything outside the red bands is actually different from 0. So let's just go through our chart and see. Lag 1 definitely is statistically different than 0 in a positive direction. Lag 2 statistically different from 0 in the negative direction. Lag 3 does not cut it because it's below the top error band. Lag 4 does cut it. It's statistically different from 0 in the negative direction. And let's say all these lags in between do not cut it, but the lag at 12, or 1 year ago, 12 months ago, does cut it, and it's very strong, okay? And let's just say that all the lags after 12 are statistically below 0, they don't cut it, so we're only concerned with these 4 that do cut it, okay? So what might a good model look like? A good model might look like, of course, we first start out with the thing we're trying to predict, which is m sub t. We have a coefficient here, beta naught, the intercept. And then we have beta 1, and of course the first lag is m sub t minus 1, plus beta 2, m sub t minus 2. Then 3 didn't cut it, so we have 4, plus beta 4, m sub t minus 4. And then we had one more, beta 12, m sub t minus 12, and we need to include the error term. So let me box this model in a different color. So put in purple here. So this, based on our evidence, could be a good model to help us predict the quantity of milk demanded today, based on the quantity of milk demanded a month ago, 2 months ago, 4 months ago, and 12 months ago. Okay? And we deduce that based on the PACF plot, which again is just measuring the direct correlation of the price of milk some number of lags ago on the quantity of milk some months ago on the quantity of milk today. That is the basics of an AR model. And the reason I like it so much is just its simplicity. Its simplicity starting from the concept of it, predicting something based on past values of that thing, to figuring out a model based on this PACF, which is very intuitive to think about. Going from there to actually creating your model and testing it, okay? This was a very gentle introduction to AR models. Of course, there's many other factors going into this, but we'll save those for a future video, okay? So, until next time.